Hello, it's Dr. Harris, and we're here ready now to talk about material out of Chapter 7 in our MAT111 statistics course. And in this chapter, we're going to be turning our attention to confidence intervals and hypothesis tests for population means. And so we've spent time in Chapters 5 and 6 thinking about categorical data, mostly proportions, also two-way tables. But here we're going to be looking at means. And so we're going to start by doing a quick review of the types of parameters that we were encountering in this course and reminding ourselves of what a parameter is. So the term parameter refers to a numerical aspect of some population. As noted here, it's a fixed number for the population. It does not depend on probability or chance, but alas, we don't know what the value of the parameter often is, usually, almost always. So what we do is we content ourselves with drawing a sample from the population. We compute a number from the sample. We call that number a statistic. We can calculate that whenever we collect the data, but we need to realize that it depends on random chance because the value of the statistic depends on the sample that's chosen. And we've also used the term point estimate as a synonym for statistic. And the idea is that when we use a point estimate to describe a population, we're assuming that the point estimate is approximately equal to the value of the parameter. We saw this table earlier. It lists the 5 parameters that we're largely studying in this course. We've already talked about the first 2 back in Chapter 6, a single proportion P, and the difference between 2 proportions P1 and P2. In this chapter, Chapter 7, we're going to be talking about the bottom 3 scenarios. Mean of a single population. Recall that we use the symbol mu, Greek lowercase letter mu, to denote a single population mean. Then in this video, we're also going to be learning about what we mean by the mean of differences, mu sub diff, and the difference of 2 population means, mu1 minus mu2. We can see what our corresponding sample statistics / point estimates are. We're going to use x bar for our sample mean, x bar diff for the sample mean of differences, and then x1 bar minus x2 bar to stand for the difference in sample proportions. So as I said, in Chapter 7, we're going to be dealing with means. And we'll start by looking at the mean of a single population. So in this slideshow, which is relatively short, we're just going to be looking at a single example of each of the types of mean situations that we'll be looking at in this chapter. Consider example research questions and come up with descriptions of what the parameters are, verbal descriptions. Also state what appropriate hypotheses might be based on the research question. So our example for a single population mean is, do students at UC Davis average 6.5 hours of sleep per night? We want to recognize that our population consists of the students at UC Davis, and the parameter, since we're dealing with numerical data, the number of hours of sleep that individual students get, we're talking about looking at a population mean. And in words, mu would be the mean number of hours of sleep that students at UC Davis obtain. Very shortly, we'll be talking about confidence intervals and hypothesis tests. But for right now, we're going to content ourselves with forming the hypotheses for the scenarios that we're looking at. And so if we're trying to talk about the mean number of hours of sleep, recall that our null hypothesis is going to be an equation. And so our null hypothesis in this case will be mu equals 6.5 hours. And we've been using 2-sided alternative hypotheses. And so our alternative hypothesis will be simply that mu is not 6.5 hours. So we're going to be testing 6.5. Is 6.5 a reasonable value for the population parameter, the population mean? And if we turn to decide that 6.5 is not a reasonable number, we will decide in favor of the alternative that it's not equal to 6.5. So we'll be getting practice with looking at verbal descriptions of scenarios, identifying in words what parameters are, when their means, come up with a good verbal description for the population mean, and we'll be able to hopefully state hypotheses based on that description as well. But now let's turn our attention to another situation where we have paired data. And so what are we going to do when we have paired data? What is paired data? So paired data occurs when we take two measurements from the same sample. So we have a single sample, but we're taking two different measurements from the individuals in that sample. And when we do that, what we can often do, what we'll often think about is that these two measurements are somehow related to each other. And so what we can do is we can calculate the difference between our observations. That's going to be our sample statistic, x bar sub diff. And the population parameter would be the mean difference across all individuals in the population. So again, two sets of observations from the same sample. We can compute a sample difference or a sample mean difference, and we'll use that to estimate the population mean difference. Here's an example. Suppose that our population is a set of University of Kentucky students, and we want to know what type of event did they attend more often in 2019, movies or sporting events. And so what we're going to do to examine this research question is we will take a single sample of UK students and we'll ask them two questions. We'll ask them, how many movies did you attend in 2019? How many sporting events did you attend in 2019? So we're collecting two pieces of information from a single sample. And so what we can do then is we can compute for each individual the difference between the number of movies they saw and the number of sporting events they saw. And so we'll compute that difference for every individual, and we will come up with, be able to try to hopefully answer the question, does that data tell us one way or the other whether or not they attended one of those events more than the other? So mu sub diff is going to be the mean difference in those two numbers across the entire set of UK students. And so that's what I've got here. Mu sub diff is the mean difference between the number of movies seen and the number of sporting events seen. We can compute the difference in either order, but we need to be consistent throughout our calculations once we make a choice as to which one we're going to subtract from the other one. Here we're going to subtract the number of sporting events from the number of movies seen. So x bar diff would be our sample mean difference for these students. What do we do about hypotheses in a situation like this? Well, typically we're checking to see if there is a difference or not. And so our null hypothesis will ordinarily be that mu diff is equal to 0. And the two-sided alternative in this case then would be that there is a difference between these two numbers and that mu diff is not 0. So again, almost every single time we look at a question like this, we're going to be checking to see, is the mean difference 0 or not? Those are going to be our two hypotheses. Then let's turn our attention to the third of these scenarios, the difference between two means. And so this is going to arise when we have two different populations, and we're going to collect unconnected samples from each of the two populations. So we're going to denote one of the populations, population 1, the other one, population 2. Each one of them will have a mean value associated with them for the numerical value that we're interested in from each population. So mu1 is going to be the mean value from population 1. Mu sub 2 will be the mean value from population 2. So just before we go to our example in this situation, let's try to, again, nail down the difference between the second and third of these scenarios, mean difference versus difference of means. So with a mean difference, we're collecting two sets of numbers from the same single sample. And once we've got those two numbers, we can compute the difference for each individual between those two numbers. And so once we compute each difference, then we can compute the mean of those differences. That will give us x bar sub diff. On the other hand, if we're talking about a difference of means, notice that we're using a different order for the words, difference of means. That means we're going to be computing a mean first. So we have two different samples, two unconnected samples from each of our two populations. We can compute a mean from each of those samples, and only then, after we computed the sample means, then we can look at the difference between them, x1 bar minus x2 bar. So again, we want to ask ourselves, is the data paired or not? Are we taking two measurements from the same sample, or are we taking two samples from two separate populations. So here's our example for the difference of means. Do baby chicks who grow up on a diet containing a linseed feed supplement differ in weight from those who grow up on a horse bean feed supplement diet? And I'll just note at this moment, that this is an exercise in our text, 7.27, page 275. We have two separate populations, two independent populations. Chicks, a set of all chicks who might possibly grow up on a linseed diet, and all chicks who might possibly grow up on a horse bean diet. So we're going to take the linseed diet chicks to be population 1. So the horse bean chicks will be population 2. So in words, our parameters are mu1, the mean weight of chicks that grow up on a linseed diet. Mu sub 2 is going to be the mean weight of chicks that grow up on a horse bean supplemental diet. That should be weight and not height. The actual parameter of interest, of course, is mu1 minus mu2. What about hypotheses in this situation? Well, again, the vast majority of the time, our null hypothesis is going to be that there's no difference in the two population means. And so our null hypothesis will be mu1 minus mu2 is 0. Whereas our alternative, our two-sided alternative in that case, will be that there is a difference, that the difference between the two is not 0. Coming up in the next video, we're going to be looking at how we can describe the sampling distribution of a single sample mean.